Welcome. You're going to witness art today. It's time to code, not for the money, but to nourish the soul. It's time for recreational programming. We are going to create a lava lamp animation. Have you ever seen a lava lamp? They contain this ultra satisfying moving fluid. You are going to witness right before your eyes how physics and mathematics help us create this organic animation. Before we begin, let me show off my website that uses this animation. Before I begin, I would set a few things straight. I would strive to keep this language agnostic, but since I'm building this for the web, I am thinking about JavaScript. Also, a huge shout out to p5.js. It makes recreational coding in JavaScript just so much fun. How do we create such an organic and fluid animation using code? If nature is our inspiration, then nature is our solution. Imagine a 2D coordinate plane. Now we place a positive charge at the origin and we fix it there. Now let's take another charge and place next to it. Now since positive charges repel, the charge at the origin would try to push the other charge away. The nearer we keep the other charge to the origin, the stronger the force it will experience and the more potential energy it will possess. How do we express this fact as a function? So as we move further away from the positive charge at the origin, the potential energy decreases or the value of the function decreases. We can simply state it as 1 over r, where r is the distance from the origin. So as we move further away, the distance increases, which is the denominator, and we get the function decreasing. Also, if we draw a circle at a particular distance r, all the points on the circle would have the same value of this function. In physics, we call these circular surfaces that are moving outwards as equipotential surfaces or having the same potential. We saw the equipotential surfaces for a single charge. Now, what if we place two charges side by side? How do the equipotential lines look now? That's the beauty. The equipotential lines look just like two cells that are going under cell division. That's something we want to achieve. If we could find a function that could describe these equipotential surfaces, then nothing like it. You would be very delighted. Very, very, very delighted to know that the function that describes these equipotential surfaces is the addition of the functions due to two individual charges. Here f of x is the potential due to the first charge and g of x is due to the second charge. R1 and R2 are the distance from the first and second charge to the point of interest where we want to measure the potential. Now it's time to put your knowledge to practice, part 1. I'm not a Jedi. Let's just jump right into the code. At first, we are going to define some constants. Just normal, which is the window inner width and inner height, so that we know the container of our canvas. Then there's a step value. This is the value which contains the distance of adjacent points. So we are not going to map all the points but a subset in the coordinate plane. Then we define a class called charge. It has a center at x, y. We also would have a function for potential which we define as 1 over r. And if you work with P5, you know about this setup function. It does what it is named about. It sets your canvas up. So we create a canvas with the container width and height. So it is full screen inside the window. Then we have this draw function. This is called at regular intervals. So it's actually called 60 frames per second. So 60 times in 1 second. Then we're going to render a grid. So we calculate the rows and columns and go over each cell one by one. We then place the charge at 150, 150. So naturally it would have a potential around it and it would have equipotential lines around it. So we calculate the field force for each of the points, which is I, j, and then we just have some rendering logic here. Let's see how it looks. So now we see the force field in action. We see that the potential function fades away as we move further away from the point where the charge is kept, that is 150, 150. It should be somewhere over here. Now let's place two charges in the grid. One at 300, 300 and the other at 500, 300. Now, as we discussed, the equipotential surfaces would be the sum of functions for these two charges. So we do just that. We sum the function as field force 1 plus field force 2. We also render it a bit differently than the previous. Let's see what the result is. Oh my goodness. This looks just what we wanted. But let's move the two charges further away. I'm going to change the distance of the first charge to 650. Oh, doesn't this look just like two cells that are trying to divide? In moments like this, I sometimes wonder, am I God?
Anyways, now we've done most of the hard work, but let's make the balls move. First, we are going to add a vector velocity. This vector velocity is going to have two components, horizontal and vertical. Next, we define the move function. As we see, the first component shifts the center on the x-axis and the second component shifts the center on y-axis. Then we add the two charges here and we give the velocity as -1, 0 and 1, 0. So both of them would move on the opposite side on the x-axis, which is defined by the first component here. Then we move the circles. The draw function is called at regular intervals, so the move functions would be also called. Our picture has turned into an animation. And now the balls are going to collide. And ooh, so satisfying, isn't it? Now it's going to hit the left wall. And hey, wait, it didn't bounce off.
We want our balls to reflect the edges. We want them to respect the laws of physics and behave as naturally as they can be. If you remember, we defined our velocity as a combination of a horizontal component and a vertical component. The horizontal one shifts the center on the x-axis and the vertical one on the y-axis. Now, if you studied physics, you know that when the ball would hit the left or the right edge, we'll change the horizontal component to face the opposite direction, but we will keep the vertical component the same. Similarly, if the ball hits the top or the bottom edge, we'll change the vertical component. And this would give a very natural bounce animation. So let's have a look at it in the code.
So we replace the previous move logic and we now change the velocity to opposite when we hit the left and right edge, and we do the same when we hit the top and bottom, but we change the vertical velocity. Let's see the animation now, and it's going to hit the left edge. Hey, it did bounce. Good, it's working. Now we add a fourth parameter called size, and then we define circles with different centers and random velocities. We also give them different sizes. Let's look at the animation now.
And we've reached the checkpoint. It's a very cool animation now. But what if we don't want this pixelated or dotted animation? We want the balls to have a smooth curvature. Then we want to change our rendering technique to something a bit advanced. This technique is called marching squares, but there'll be a whole another video. So if you found this video inspiring, you know the drill. Like, share, subscribe. The more like it gets, the faster I'll upload the follow-up video. So stay curious and sometimes do things which are not entirely useful. And I'll see you in the next video.